So yeah, my name is Arthur Perez, and I'm currently a master's degree student at Imperial College in London. And today I'm going to deal with a part of my master thesis, which is about high temperature fracture toughness test on P91 steel for nuclear fusion applications. But before we start, I'd like to share three main advances in the world of nuclear fusion. First, in July 2021, the joint European torus produced 59 megajoules of energy while burning less than 200 micrograms of deuterium and tritium. A year after, an American laboratory reached the ignition threshold, which means that they recovered all the energy they used to provoke the fusion reaction. And 3 months ago, in south of France, a reactor produced plasma at 50 million degrees for more than 6 minutes. So it takes time, but it looks like fusion has everything to be promising in terms of production of energy. But what is nuclear fusion reaction? According to the International Atomic Energy Agency, it's when two light nuclei combine to form a heavier one with like a huge amount of energy released. And to do so, we need reactors. And to have reactors, we need some structural materials with some properties, such as being able to handle thermomechanical loadings or having low activation properties, for instance. My project is in partnership with the UK Atomic Energy Authority. And they, at the beginning, wanted to focus on a material called Eurofer 97. But because this material is scarce, we did the test on P91 steel, which is quite a similar alloy with similar properties. So now let's move on the technical aspect of my presentation. After presenting the experimental procedures, we'll talk about my results of the fracture toughness test, including some FE modelings. So I did my test at 600 degrees. When we do a fracture toughness test, what we want to know is the ability of a material to resist crack extension when it is subjected to a load. It is important to know this property when you want to design a component, when you want to do a benchmark between many materials, or when you want to forecast the behavior of a material. And how do we quantify the toughness of material? Well, we can do a JIC test, and this is what I've done for my research, that evaluates the energy required to propagate the growth within the crack within the material. And on the right-hand side, you can see an example of a JR curve we might expect to obtain at the end of the test. And we'll see later on if I manage to obtain this curve. The motivations for my project, well, my work follows on what a former PhD student did at Imperial College. He did some fracture toughness tests on really small CT samples made of P91 steel at 600 degrees. And he found quite low JIC values. I plotted the evolution of the toughness as the function of the thickness of the sample. And what is worth to remember is that the thinner the material, the higher the toughness, and the thicker the material, the lower the toughness, with plane stress condition with thin materials and plane strain conditions with thick material. So as I said, I did my toughness test at 600 degrees on CT sample made of P91 steel. They were quite thick, 25 millimeters for the thickness, no side grooves, because like the really small samples the PhD used were not like using side grooves. The width is 50 millimeters and the initial crack length is 25. The setup. So before any test, I pre-cracked all my samples by fatigue to a crack length of 26 millimeters. And I used basically 3 methods to monitor the crack extension during the test. First, the DCPD method, so direct current potential drop method, then the compliance method. And finally, I did some digital image correlation analysis using a camera, taking pictures through the window of the furnace. So only one camera has been used, so it will be like a 2D DIC analysis. Here's an example of a sample I just obtained after the test. It is quite obvious, like there's a huge plastic deformation zone here with like a huge contraction effect and kind of shear banding. It is worth to remember that I had high temperature, the stiffness of a material decreases while the ductility increases, and overall the resistance to plastic deformation decreases. So this huge zone might have an impact on my results, but I'll show you later on. I opened entirely all my samples by fatigue to analyze the fracture surfaces. And what I observed is instead of having like a straight line for the crack propagation, it was like more about like what we call a channeling effect. That is to say the shape was more as a parabolic shape. And also this is the second point that might explain the result I'm just about to show you. So the three first samples were tested using DCPD method. So here is the load versus displacement curves. They're quite all the same shape. And on the right-hand side, there's the PD voltage against displacement, where we can find our V0 value. According to the standard, this value is like when the crack initiates. And instead of using the shape function mentioned in ASTM, I used another shape function developed by another former PhD student at Imperial College, which found it to be the best to describe our type of test. And here are my three first JR curves. They all give a JIC value around 315 kilopascal meter, and so they all seem to agree. My fourth test was using compliance method, more particularly unloading elastic compliance method. And after 21 cycles, here's the JR curve I obtained with a way much lower JIC value, around half of what we found just before, around 150 kilopascal meter. And this is the summary matrix with all the results of my four tests. Regarding the literature, so there were like few papers available on high temperature fracture toughness test at 600 degrees with material as thick as the one I used. So they do agree more around this value of JIC, more around 300 kilopascal per meter. So something went wrong during the experiment using compliance, maybe like a misalignment with the clip gauge. It was hard to really follow the test because it was like obviously in the furnace. So maybe there was like something wrong during the experiment. So we'll just have a look on the three values. And then I wanted to see if my values were in a good agreement with like the physically measurements. So when I opened entirely my samples, I did measure the final crack extension. And so here are the final crack extension I measured physically. And they are like way lower than the one predicted by the four JR curves I've just shown you. They were predicting more about 6 millimeter, and we are like sometimes not even at 1 millimeter. So what I did is instead of using the shape function that I mentioned, I used this expression relating the voltage to the crack length, and AF, my final crack length, and my initial crack length are the one physically measured. So I could like replot my three first JR curves, and the results are like way different. With like, for instance, the first test, JIC value around 600 kilopascal per meter, almost an infinite one for the red curve. Like, I don't know when it will cross the 0.2 line. So for me, what can explain these curves is, as I mentioned, the two phenomena we saw, like physically. That is to say, the huge contraction effect on the sample, and also the tunneling effect, because the standards do assume that the crack extension will propagate as a straight line, but we saw that it was like more about like a tunneling effect, like more a parabolic shape. And so these two main issues might explain the difference between the actual physically measured crack length and the predicted one. Finally, I did some DIC analysis on a sample. Here is the strain field at the very end of the test on a P91 at 600 degrees. So what we can see is quite in a good agreement with what we could expect. That is to say, the highest strain values are around crack tip. I checked it with like an Abacus simulation using also the same material properties. And they do give almost the same maximum value, around 10%. So it is in a good agreement. And finally, I did a stress intensity factor analysis simulation on Abacus to see if there was like in a good agreement with the prediction. So for the three first values I said we're going to focus on, they are quite in a good agreement, like a relative difference less than 15%. But once again, Abacus, DIC, these are 2D models, so they do not take into account the thickness, the influence of the thickness of the material, the huge shear banding that we saw, and also the tunneling effect. So what can be done next is to work and to find some other models to predict and include the effect of the toughness, of the tunneling effect. Also what we can do is to consider side grooves on the sample, because obviously side groove might reduce the effect of the contraction, but because we wanted to do a continuation with what a former PhD did, we didn't use side groove, but it can be a further work. Thank you for your attention.